In this video, we're going to talk about the use of the force model with a side dish. That occurs when one of the forces acts at an angle to the x or y axis. So here we go. So this is the problem we're going to have. The Magic Blue Bus is traveling down the street and it's accelerating because we're going to the physics party. And there's a set of dice on the rear view mirror. And because the car is accelerating, we're going to accelerate in this direction here. This die or dice makes an angle theta with the vertical. This is the vertical here. It makes an angle theta with the vertical. So it's backward because the Magic Blue Bus is accelerating to the right. So the question is, given the angle theta, what is the acceleration of the car? Because the more you accelerate, the further this will go back, and if you were to be at rest, then there would be an angle of 0 here. So what is that acceleration rate? So the first thing to do again is to draw the free body diagram. So I'm going to draw the die that's on the rear view mirror here, and we have mg pointing down as it always does, and a tension T at an angle. Okay, so we actually draw it at an angle to the vertical. Okay, and there we go. That's our free body diagram. There's nothing else acting on it. So we are going to now sum the forces. So I'm going to state the positive direction is to the right and the positive y direction is upwards. Okay, so this these two forces we're going to put into the force equations, but tension actually, because it's at an angle, has a x and y component. Mg is easy, it points straight down, but T is at an angle. So we need to do a little side dish here. So I'll say step 2b, side dish, to break those components up for the tension side dish. Okay, so I'm going to draw my tension here, T here. Now we're going to be a little careful because the angle they give us is this angle here. And what I want to find is, if I drop this perpendicular down, is the x component of the tension and the, if I draw this across here, the y component of the tension. So I want to find these two components because those are the components I'm going to put into the force equation. So if I'm careful here with the angle, I can say, let's see, I'll just say sine of theta. Let's see what it gives me. Sine of theta is equal to the opposite, so that's the x component of the hypotenuse, and the cosine of theta is the adjacent right here, or the y component of the tension. Okay, so now I know what the tx and the ty components are. So now going back to the step 2 here, I'll say that in the x direction I see a tx, which is really t sine theta. The x component is t sine theta, and it is accelerating, so I'm going to put a x here because it is accelerating. And in the y direction I see a t, let's make sure it's t cosine theta, which points upwards, minus mg, and it's not accelerating up or down. Okay, so whenever you have a situation where the one or many of the forces are at an angle, we need a side dish to break those components up according to their sine and cosine components, and those are the components we're going to put into the force equations, keeping in the theme that x and y forces are independent. Okay, so now that we have our force equations, now we can try to solve for that acceleration, and specifically this acceleration right there. So the equations that I get are from the force equations: t sine theta equals m a I. Okay, and I have t cosine theta minus mg equals 0. Okay, because it equals 0 there. So let's see, the unknowns that I have are the tension and acceleration, and over here I have tension as unknown. So I have two equations and two unknowns, which is good. So it looks like what I'm going to do here is, if I call this step single I, just writing them down, step 2I is I'll solve for t. So t is equal to mg over cosine of theta, All right, and once I know what t is, then I can plug t back in, into the first equation, or the x equation, to solve for the acceleration in the I direction. So step 3 is going to be mg over cosine theta times the sine of theta, so there's a tangent sitting there, equals ma, and the m's cancel. And it looks like, and I'll just do step 4 over here for lack of space. On your homework, you'll have a little more space. A is going to be equal to, looks like g tangent of theta. And there's your answer. So again, what I did was I followed the same procedure. I drew an FBD. I summed the forces. However, one of the forces acted in an angle, so I was careful to go to the side dish and break that force up into x and y components. And you're going to need one of these for every force that's at an angle. So if there were multiple forces at an angle relative to our normal x and y axes, you'd have to do that. Plug those back into the force equation, and then from there you have your force equations that you can then solve with. So there's an example of the force model with a side dish.